put initial condition in there, and we can find the C value. Now, okay, so Macy said, she said an antiderivative. That's how that one can be solved, is an antiderivative, right? That's how we can find the original function. But in this one, so back to this problem, can we do an antiderivative on that one? So now back to my original question, why can't we right now solve this differential equation? Because there's a mixture with an x and a y in there, right? Or if it was just a y in there, if this was y prime equals 4y, we couldn't do it either. Now, we actually memorized that one. Remember, we had the y prime equals ky. Do you guys remember? This is all good stuff because we were going to review this today anyway, here in a minute. What's the solution to one that looks like that? AE. It's an exponential. It's y equals AE to the kt. So if this was y prime equals 4y, we could do it right now. Right? If this would have been y prime equals 4x, we could do it with an antiderivative. If this would have been y prime equals 4y, we could have done it because we memorized it to be AE to the kt. But since it's y prime equals 4xy, we couldn't do this. And remember, we kind of listed it as 3 different types of differential equations when we did it. Remember, the ones we could solve with just antiderivative, like the 2x one. The one we memorized, like this one, and then we had Newton's law of cooling. Remember that one too? We had Newton's law of cooling. And then the third type was like a mixture of x's and y's, ones we don't know how to solve. Okay, so good. We got our review out of the way a little bit here with differential equations, okay? But anyway, that is why we can't solve this. We will be able to solve this, though, after we get through chapter 7, okay? So that's something we'll get to later. All right, another one. Another one. 22. Okay. We've got a definite integral. It's got that dreaded k in there. That always gives us some grief. And remember my advice, just work it and pretend it was a number. Just pretend it was a number. Do everything you'd normally do if it was a number. And they do tell you something about that, which may come in handy here a little later. But what would we normally do if that was just 0 to 3? And this is no calculator, right? So if this was 0 to 3 or whatever, what would we do? Antiderivative of cosine is sine. Leave the inside alone always when you do any derivative, antiderivative, whatever. We got to do something with that 2x. Kick out a what? A 1/2 because we're doing the antiderivative, right? So we kick out a 1/2. And then we would go 0 to k, right? We would plug that in. So we put our k in. We get 1/2 sine 2k minus 1/2 sine 0. And of course, that's just 0, right? That's just 0, so that's easy. So 1/2 sine 2k. Of course, now we got to do something with that k. Oh, it equals 1/2. It equals 1/2. So we can multiply both sides by 2. So we got sine 2k equals 1. So now we got a little bit of trig going on here. So we're done with the calculus, right? Calculus is over in this problem. Now, again, in the multiple choice, they want to test you on your algebra, your trig, stuff like that. So forget the 2k for a minute. Where does sine equal 1? Pi halves. If you went around again, it would be what? 5 pi halves? Not that we're going to need that, but I thought I'd just throw that in there. Okay. So this in here has to be pi halves. So 2k has got to equal pi halves is what that means. Right? So k would be pi 4s. K is between 0 and pi, so that just means we're one time around here, so that's no problem. So that works. So there it is. Okay. There it is. So a little bit of trig there at the end. Whenever you have some other stuff on the inside, you still ask yourself the question, where does sine equal 1? That's at pi halves, and that means that thing in there has to equal pi halves. And so then you just set up a little equation and solve that. All right. Anything else? 26. We cannot. Okay. The volume of the solid of cross sections, one of the things we're going to learn in chapter 7. When we do our famous lemon slicing lab. We can actually cut lemons. Probably have to get a permission slip from everybody if it's okay to handle a knife. Probably get still waiting to get in trouble when I do that lab. But anyway. So 26, what's the right answer?
Yeah, I thought I did it, but maybe I did not.
I would say you did not. Because I think about all the things you have to do on that one. But let's look it up, maybe. You never know. What'd you get?
I got
E.
E.
26.
No, probably not. But I was like, oh, I got an answer that's on there.
Anybody else get an answer? C. Did I hear A? Who got A? Answer's A. I'm going to look at what he did. He Googled it. I'm sure he Googled it. He just typed it in.
Looks legit.
Looks like I don't know what I'm looking at, but it looks. He's got a lot of work there down there. Where in the world did you get all that? Be honest. Did you really?
Yeah.
That is so cool. You know, the other day I was. It is. I mean, what you could. Did you just type the whole problem in?
Yeah.
I think it's maybe
Did it have? It is A. Did it have? Did it have? Was it a pretty good explanation, like a picture and stuff like that? Not really.
It showed like half the way.
I wonder if it was from this exact like worksheet, or did it? It didn't really say. There's all kinds of cool. When we do this, there's all kinds of cool animations and stuff on the internet. And actually, I've got a program that shows some really cool animations. But
I didn't do it. I asked.
but anyway, yeah, that's something we're going to learn in. That's something we're going to learn in chapter 7. Okay. All right. Any others?
No, it's 25.
Oh, 25. You want to see?
19.
Okay. Now this means, what does this mean?
Second derivative.
Second derivative, y double prime. Okay. So this one's going to be a couple of implicit differentiation situations. Now, actually, this one is written in such a way that you can do this without, you could shortcut it. Now, I'm glad I noticed that, because I would have worked it out the long way, and then Maddie would have said, well, I do this. Maybe the bad. But you know what I mean? Aren't those like terms?
Yep.
And it, just the fact that they kind of rearranged them, you know, tried to throw you off. It's really yx squared plus yx squared, which is 2yx squared equals 6. And can't you solve that for y? So you divide by 2, you get 3 over x squared, which would be 3x to the negative 2, right? So now your y prime is just negative 6x to the negative 3, and your y double prime is 18x to the negative 4, which is 18 over x to the 4th. And then you put in your point. So you put a 1 in for x, and you get 18. You were close. But now, they wouldn't have had to change that problem much, and then you wouldn't have been able to do that. Like if this would have been a y squared. Then all of a sudden you can't solve for y, and you'd had to do a bunch of implicit differentiation. Then you'd had some y primes in there, and they had to do the derivative again, which you use some y double primes, right? And you'd have to do all kinds of different stuff. It would have taken longer. So the fact that you could add those together as like terms and get the y by itself really made things easier. Okay, but recognizing that is hard, because I'll be honest, I was first thinking of different implicit differentiation. So, okay, 19. Let this be a differentiable function. Okay, good. We've done a bunch of table stuff here lately, a bunch, but coming back to it and seeing how it looks on the AP test is important. This is f and f prime, so it's differentiable. F's differentiable, so the function, so it's continuous. That means the f values exist everywhere. They're defined everywhere. It means a derivative exists everywhere, right? And so differentiable function, that's good. You know there's not going to be any undefined places on f, not going to be any undefined places on f prime. So it's all good from that standpoint. So that's good when they say that. So the line tangent to F and parallel to the segment between the endpoints intersects the y-axis at the point what? Okay, so think of it this way. So in other words, we've got, if we plotted all these points, and here would be the endpoints, let's say, we want the slope between there, right? And then, but that, if that curve does something like this, then it's kind of that mean value theorem thing, right? Then we want to find the line that's tangent to that, that's parallel, that has that same slope. Okay? So, you guys tell me, where should we start with this? I've given you a little bit of a hint of what we want to do here. Slope between the endpoints would be the first thing you want to do. So here's your endpoints right here. Right? So we're going to subtract those. 26 take away 2, negative 2 take away 10. So that's 24 over negative 12, which is negative 2. Now we want to see where does that graph have that slope, right? Because we want it to be parallel. We want to find the tangent line, which is parallel, which means where the derivative is negative 2. Well, that's right here, right? So what do we got? We got a slope is negative 2, and we got the point is 423. So all we need is the equation of that tangent line. So it's just another way, but different than we've ever seen before, but just another way of doing a tangent line problem. Which, remember, what do you need for a tangent line? You need slope, you need a point. Well, since they told us it was parallel to the segment between the endpoints, we had to do the slope between the endpoints to see what our slope was, negative 2, and then what point was it that had that slope, and that's 423. And now we just go y equals negative 2, x minus 4, plus 23, and then work it out. And they want to know where it intersects the y-axis. That's like your y-intercept. So negative 2x plus 8 plus 23 is y equals negative 2x plus 31. So which one's the right answer? Y-intercept is 31, right? So again, it's just a lot of different ways of asking a lot of the same questions, right? A lot of the same questions that we've talked about. But if you really understand what's going on, you should be able to see it in new situations and not be too thrown off. More so now, but a month from now, we want to have seen a lot of these, and that's why we do the packets. Okay, moving on. Get your notes out. Let's go ahead and get to this so we can have a little time to get started on stuff today. All right. So good to have your calculators out here at some point today too. Don't forget, some of you were looking at this. Don't forget tomorrow to have your Niobrara assignments turned in. And then we got our quiz on Friday. So tomorrow's going to be in class. We'll have some packet time. We'll have some review time. For you to be working, and then okay, all right. So the review part first. So we already talked about differential equations a little bit. So we've obviously got some differential equations we do not know how to solve, right? We talked about that earlier when you guys were asked about number 20. So then we did something called slope fields, and we did that because we wanted to be able to do the solution to a differential equation that we didn't know how to solve. We wanted to, is there a way we could approximate? Okay, there's a key word. See why this fits in with what we were doing with areas, right? What have we been doing in section 6.1 and 6.2? What have we been talking about? Approximations to integrals, to areas, right? Left, right, midpoint, trap. But specifically, we've been talking about error and max error and that stuff. But we've been talking about approximations. We've been talking about these definite integrals we don't know how to solve because we don't know how to do their antiderivative, right? And so we're investigating ways of doing approximations and how accurate they are and stuff like that. Well, guess what? Same thing with differential equations. We have some differential equations we don't know how to solve. That is, we don't know how to find the original function y. So earlier this year, we used slope fields as a graphical method to approximate some solutions to differential equations. So let me remind you a little bit of what a slope field was. Now, what we're going to learn today is something called Euler's method. Euler is how you pronounce that. It's not Euler. It's not Euler. I know, it looks like Euler. It's Euler. I don't know that French.
Sounds like German.
German?
Yeah.
German. I don't know, it probably says it. Leonard? Is that a German name? Leonard Euler. Maybe it's Swedish. All the famous men. Oh, yeah, all the famous mathematicians were Swedish. All right.
The John Smith.
Does it say? I've got a PowerPoint. Switzerland.
Or Johnson.
Close, isn't it? No. Is that even close to Sweden? It starts with an S. That's about it. It starts with an S, W. That's about it. He was born in Switzerland. It says. All right. So, anyway, so the new thing we're going to learn today, Euler's method, is a method for numerically solving differential equations that we don't know how to solve another way. In other words, there are still approximations, as you're going to see. Now, slope fields were a graphical way of approximating. Euler's method is going to be a little better way of approximating. Now, if you remember, we're going to do this. You might jot this one down in your notes here. If you remember what we did when we first did slope fields, we've gotten progressively better at approximating these things. Okay? Because what we did when we started is we said, remember in chapter 1, we said, remember in chapter 1, when I gave you an F prime graph, we'll just do a real easy one, and you had to draw the F graph. Remember that? Gave you an F prime graph, and you had to draw the F graph. This would be good chart review. So starting over here, what do I care about on this F prime graph? It's positive or negative, right? And so over here, this is positive and pretty good positive, right? So what is my F graph doing? Going up and fairly steeply, right? Now, do I know where it is? Remember that was that plus C part, right? I don't really know where it is, but let's say it's like here. And it's going up. But what's happening to F prime? Less positive, less steep. And so it's going like so. And what's happening right here? Local max. F prime changes from positive to negative. So F changes from increasing to decreasing. And then it's negative and getting more negative, and it's going down like so. And we got a parabola, right? Something like that. Not a very good picture. But right? Now, was that a very good representation of F? Back up. Is that, did I just solve a differential equation right there? Well, think about it. What did I start with? F prime. And what did I end up with? The original function F. Did I just solve a differential equation? In a manner of speaking, I just solved a differential equation, right? Is it a very good solve? It's a possible F, but anytime you solve a differential equation, there's a plus C, right? So you've got, it could be anywhere shifted up and down, right? But is this a possible solution of this differential equation? Yes. Is it a very good or accurate one? No. I mean, it's a mess, right? And if I wanted to find F of 2, right? Now, let's take it one step further. let's say I had added into this f of 0 equals 2. Let's say I had given you this graph and told you this about f, an initial condition, an IVP, an initial value problem. Then I would have known, okay, that f is going to go right there through 2, right? Now this is better. This is a more specific solution, right? Would you trust this very much to find f of 2? Right? I wouldn't trust this f graph very much to find f of 2, right? It's a very, very weak approximation, but not awful. It's got kind of the general shape of it, but graphically, okay. So that was where we started. And then when we did slope fields, we said, you know what, we can do better. We can do better than just do that. And not only that, but we can do it with all kinds. Like we can do it with one like this. Right? I wouldn't be able to graph this, right? I can give you an f prime graph, but that would be like f prime of x or something. This, I can't graph that as an f prime graph when it's 3y, right? That would be weird. So, I mean, I could pick some different y values, I suppose, but that's what we did here. We said, well, let's plot some points. Like, let's put a 0 in for y. What do you get for y prime? So that means any time that y is 0, which wouldn't that be here? Wouldn't the slope be 0? Right? And let's put a 1 in for y. What do you get? So doesn't that mean that any time, remember slope fields? Just ringing a bell at all? I hope. Okay. Right? Doesn't that mean that any time y is 1, remember we talked about columns and rows of slopes that were the same, and you could tell if your y prime had just a y or just an x, right? We did matching. We did matching of these slope fields. And if I put a 2 in for y, that would be 6. That's really steep, right? And some of you might be recognizing, oh, wait a minute, this differential equation is one we memorized, isn't it? Wouldn't it? What would the solution to this be? AE to the, not K, 3t, right? Because that's your K right there. Right, to be 3t. Just be AE to the 3t. So this would be our slope field. What about a negative 1? What happens if we get negative 1 in it? Negative 3. So we'd have slopes like this. Right? Like so. And we would need an initial condition. And let's say I gave you y of 0 equals 1. So that would be right here. Right? And so then, now it'd be nice to have some more points, but we know since it is an exponential, it's going like this, and it's going like this, right? And there's our solution. Now that's a little better. So if I have enough of these little slope segments, remember we could just kind of sketch it in there, we'd go with the flow. Now don't you feel a little better about that red graph than maybe the one I did over there, right? Because we literally plotted some points. Now we didn't really plot points, but we plotted slopes, right? So we actually plugged some numbers in to our differential equation, got the slopes of y, and we were able to kind of see it, and we were able to plot our solution curve. Now, it's still not real great. I'm just kind of trying to follow those things. If I wanted to find y of 2 right now, or y of 3, I don't really have a y equation I can plug into here, right? I haven't found a way of solving it. But, and we will learn it in Chapter 7, but graphically, I could go over to 2, and maybe I could get a reasonable estimate of what y of 2 would be. Well, okay, what we want to do today is do better than that, even. We want to make this even better. And we're going to do this thing called Euler's method, and I think you're going to notice how it's really well connected to what we've been doing with areas. Okay? All right, so we're going to do this problem right here. So we're going to do this 2 ways. And we're going to have very much the same rules we had with our rectangles. We're going to start with y prime equals 2x, which of course we know the exact solution to that, right? We did it a little while ago, right? And we're going to start with the initial condition y of 0 equals 1. So this is an IVP. It's a differential equation with an initial condition attached. Okay? Well, we know the exact solution to this, of course. Y is equal to what? Plus C. Then we put our initial condition in, put a 1 in for y, put a 0 in for x, and we get C equals 1. So we know the exact solution to this is that right there, right? So what is y of 2 actually? Y of 2 is actually 5, isn't it? Right? We know in this differential equation, we actually know the exact answer. That would be the equivalent of doing a definite integral where we actually could do fundamental theorem and find the exact area, right? But then wanting to try and do 10 left rectangles or 5 right rectangles or 50 midpoints or something and see how close we were, right? Now, we're not going to get into error and all that stuff with this, but that's the idea of what we're doing. So we're going to do, using Euler's method, here would be the directions you would have. And so on Friday's quiz, I might give you a problem like this, and I might ask you to do these two things right here with this problem. Now, the first one we're going to do by hand, 4 steps to find y of 2, or to approximate y of 2. And then 10 steps. Now, the 10 step, you're going to get to use your calculator, right? Remember with rectangles, if it was double-digit subdivisions, you get to use that little program. Well, same thing here with Euler's method. If it's double-digit numbers of steps, you're going to get to use your calculator. Now, there's not a program. We're going to actually graph it, and you'll trace, and that's how you'll get it. You're going to see that in a minute. But the first one, 4 steps, since it's single-digit, we're going to do them by hand. Okay? Now, eventually, we're going to write out a table here of how to do this, and I'm going to show you how Euler's method works, so we're going to go through that right now. How does Euler's method give us an approximation of this numerically to help us to do this? All right, so all right, I don't know what that picture is. I stole this from a math teacher by the name of Greg Kelly. Okay, there is Mr. Euler. That is a funny hat. It's sort of towel kind of a thing. That is weird. Yes. So you can see he lived in the 1700s, kind of the, that Newton, Newton was more in the late 1600s, but that Renaissance time period where a lot of different mathematical discoveries were going on. A lot of the Pascals and the Newtons and and those kind of things were happening. He's quite a, there you go, Swiss mathematician. Made a number of contributions to mathematics, almost half after he was totally blind. When this portrait was made, he had already lost most of the sight in his right eye. He still don't say what he's wearing on his head, though. Maybe that's why he was blind. He couldn't tell. Imagine what. Yeah, he didn't know. Whatever. All right.
That was probably a joke. Here, this is
put this on your head. That's awful. It was Euler who originated or popularized the following notations. F of x. He is responsible for our function notation. Naming that E. You guys don't like him already. E. But imagine if we didn't have that. It could be worse. It could be harder. It was probably made things simpler when he did this. Square root of -1. Calling that odd. I'm not sure. This doesn't mean necessarily he was the first one to use that, but he's a lot of times what happens. A lot of different people were doing a lot of the same work. It was kind of who published it first and who kind of got credit for it, and so forth. Sigma notation, using sigma to mean a sum. And this is going to come into play here. This idea of delta y, delta x, the change in using that delta to mean change, and pi. So that's a pretty good list right there. Okay? All right. And then, of course, like I said, it says the Python was first used by somebody else. Whatever. However, the symbol was not in common use until 1748 when Euler used it in that paper. All right. So anyway, there are many differential equations that cannot be solved. We can still find an approximate solution. We'll practice with an easy one that can be solved. So we'll start with y prime equals 2x. With an initial value y0 equals 1, which is the one we did a minute ago, and here we go. So if you want to kind of copy this into your notes, it's not a bad idea, okay? Because we are going to do another example then, very much like it. In your homework, you're going to have a couple of them. Again, in your homework, you're going to have a couple of them you're going to have to write out by hand, and you're going to have a couple in there that you can just use your calculator and trace and do. Okay? So we want to solve this. So this is the y graph we're trying to graph. Now that's what we were doing up here. We had started with f prime. We were trying to graph f. That's what we did with slope fields. We started with a y prime, and we were graphing the y graph, the solution. We were doing it graphically. So we're going to do a little bit graphically here to connect it. But the table that you're going to see him draw here in a minute is the key. All right. So we're going to start with these values. Okay, I usually don't label that first one n. To be honest, I don't even do that first column. So if you want to leave off the n column, you can. So I usually start with an x column and a y column because that's going to be our initial condition. That's our starting point. Okay, so we're going to start at the point 0, 1. Okay, so we're going to start with the point 0. So again, just forget that far left-hand column. That's number of subdivisions, I guess you might say, number of attempts. So we're going to do 4 steps here, right? We're going to do 4 steps. Okay? So, plot that point, 0, 1. Okay, that's our starting point. So that's the one point on y that we know. The only one. But what we do know is the slope, right? So here's the key now to Euler's method. So the next column is going to be the slope column. You can just write y prime if you want, or dy over dx, either way, doesn't matter. So the next column is going to be the slope column. So what is the slope at that point? Well, we can get it just like we did with slope fields. We just plug it in, right? So plug in to the y prime equation. What do you get? 2? Get 0, right? Because you're going to plug in an x this time, right? So you're going to plug in an x. X is 0. 2 times 0 is 0, right? We're plugging it in right here, okay? And we get 0. So at this point, the slope is 0. So if we were doing a slope field, we'd draw a little horizontal segment there, right? Now, does the graph stay horizontal? No. Now let's stop just a second and think about areas when we do left rectangles. If I go up on a graph to a left rectangle, and I go across to draw my left rectangle, what kind of graph will that fit perfectly? Horizontal, right? Does the graph stay horizontal usually? No. So when I go across like that to make my left rectangle, I'm off because the graph doesn't stay horizontal that whole time, right? Now, how do we make our approximation better? Use more rectangles. So, in other words, if I'm not using very many rectangles, like on this picture here, if I go up and then go way over here and then down, I'm assuming that graph stayed horizontal that whole time. It's not going to. So it's going to be off. So the same thing's happening here. I figure out the slope at that point. And then what we do is we say, well, let's go with that slope for a while. Now, how far we go with that slope is dependent on how many steps we're going to do. It's kind of like the width of the rectangles. So look at this down here. Now, let's investigate this a little bit. dy over dx, that's a slope. That's rise over run. Times dx. dx, let's call that the run, right? Well, what's rise over run times run? The rise. That's what that is saying right there. If we take the slope times the run, we'll get the rise. So that's what the next column is going to be. Oh, okay. Now notice the next thing they put up here is this right here. The dx, or call that the delta x. Also think of that as the run. Well, why is that? Because we're trying to go from y of 0, and we're trying to find y of 2, right? So we're trying to go over from 0 to 2. You don't have to write this part down. And we're going to do, how many steps did we say we want to do here? 4 steps. Does that look familiar at all? Isn't that what we do with rectangles? Don't we do b minus a over n? That's the same thing here. It's the same thing here. This is often called the step. When we're doing Euler's method, we actually call it the step size. But it's really just the subdivision. It's really the delta x is what it is. It's really the delta x, but we call that the step size. So in this problem, 2 minus 0 divided by 4 is 1/2. That's our step size. Okay? So That's all kind of the same thing we're doing. The difference is we're not doing the area from 0 to 2, but we're starting at y of 0. We're starting at y of 0, and we're wanting to figure out y of 2. That's what we're doing in this problem. So that gives you your b minus a. We're going from 0 to 2. Okay, and we want to do that in 4 steps. So each step has to be a half. It's the run, the step size, the delta x, whatever you want to call it. Okay, so the next column in this is going to be our rise. That is, now you might want to make a note to yourself in your table that this is the y prime times the delta x. That's what you're doing. You're taking the y prime, the slope, times the width. But that's like taking rise over run times run. So that gives you rise. Okay? You might even write that in, rise over run times run. And that gives you rise. So that's what that column is right there, is the rise. So that, now this is easy, because obviously if the slope is 0, we're not going to rise, right? We're not going to go up. So, then this last thing, I don't know if you need to write this down here, but what I usually do here is I think of this is my new y right here, yn plus 1. Well, that's my old y plus my rise, if you think about it, right? My new y. So what we're saying is, we're starting at 0, 1. We're going to go over how far? We're going to go over a half, and then we're going to go up how much? Well, it depends on the slope, right? This all depends on the slope, so that's what that is. So we're saying, okay, we're going to start at 0, 1. Let's figure out what the slope is there. Let's assume it keeps that same slope the whole time, and let's go over a half, and then, of course, this time we're not going to rise at all because the slope is 0, right? But let's go over a half, and let's figure out how much we go up. And then we're going to go over a half, whoops. We're going to go over a half, figure out how much to go up. We're going to go over a half, figure out how much to go up, right? That's what we're doing. So we're taking what we did with slope fields, and we're taking a step further. We're actually calculating the rise and the run with the slope instead of just drawing those little slope segments and estimating. So it's a better estimate. Okay? So the next column you have here, I call it the new y. I usually call this just the new y column. But if you want to jot it down in there, that's the old y plus the rise, or the previous column, the delta y column, the change in y. Okay? So the new y is going to be 1. We're not going to go anywhere, right? So we're going to go over a half. So now look at the next column, okay? So or look at the next row now. Again, forget that left-hand column. So the next point we are now at is a half. We went over a half, and then we didn't go up at all because the slope was 0. Okay? We're going to have, how many rows? We're going to have 4 rows.
And is that as many columns as we'll have, just 5?
Those are all the columns we're going to have right there. Oh, you ran out of room? Okay, yeah. Nope.
Wasn't sure how to space out.
That's all you need. I'm sorry. I should have told you that. Okay? All right. So now we're going to plot that point. Okay? Now, when we do these, we're not going to actually graph. Okay? In this one example, we're just doing the graph, just so you see what's going on. Okay? Now, we know the answer to this. What is the solution to this difference equation? It was 5, and what was the equation? X squared plus, and it was 1, right? So we actually know that this is going to be at 0, 1, and it's going to curve and go up because it's a parabola, right? So we actually know this goes like this. It doesn't go like that, right? But why is our graph going like that? Because we're doing an approximation. Because we're assuming that the slope is going to stay 0 that whole 1/2 width, and it's really not. The slope is changing, right? The slope is y prime equals 2x. So every time x goes over just a little bit, that slope gets steeper, gets steeper, gets steeper, gets steeper. But we're doing an approximation, just like we do with area. So Euler's method figures out the slope, assumes it stays that slope for a while, and then plots a new point. So we now have a new point there, 0.51. Now let's calculate that slope. So now let's calculate that slope. What do? We take our 0.5, our x, and we plug it back into our y prime. What's 2 times 0.5? 1. So at this point, our slope is going to be 1. Now that's easy. What are we going to do? We're going to go over how much? 0.5 and go up how much? How much you go up if the slope's 1? You go over 0.5? Up 0.5. But it won't always be that easy, so let's just go through the calculation. So what do? We calculate the slope. It's going to be 1. Then how do we get this column? Take our slope times our run, right? Rise over run times our run. That's going to be 0.5. So we take 1 times 0.5. So you got to understand what you're doing in each column. You can make little notes to yourself, and that's helpful, right? But you got to understand what each column is doing. It's just a way of organizing our work. It would be, we wouldn't have to make this table, okay? But it's just a way of organizing our work. With simple problems, this probably seems like more work. With harder problems, it definitely helps, okay? All right, so our new y is going to be 1.5. So we were at a y of 1. We were at a y of 1, and now we're going to go up 0.5. So our new y is our old y, 1 plus 0.5, our delta y. So we're now at 1.5. So we write that down here. So we're now at the 0.1, 1.5. Now, you know what I usually do in these problems? Since I figured out, remember at the beginning of our width problems, we always figured out delta x right away, our area problems, right? We always figure out delta x. Once I know my width is 0.5, I usually fill in this column right away. I go 0, 0.5, 1, 1.5, and 2, right? Because that's what we need to do. Now, I said we're going to have 4. We're actually going to have, at the end of this one, we'll know. At the end of the fourth one, we'll know. But I usually fill in this right away, because then I don't forget what's going on. So I know I'm going to go by 0.5. So 0, 0.5, 1, 1.5, 2, right? And so I fill that in right away. All right, so let's plot that point. So 1, 1.5, and we connect to that. So it looks like that. Okay, now we know the parabola doesn't actually do that, but there we go. Okay, and we just keep repeating. So y prime, so we're going to plug our x in, and we get a slope of 2, right? So our slope column we get from our differential equation. We'll always know it because it's a differential equation. We're going to know the derivative. That's what we're given in a differential equation. It's an equation with a derivative in it. So we get a 2. How do we get this column? Take 2 times the run. 2 times 0.5 is 1. That's our rise. And then how do we get this column? Our new y is going to be our old y plus our rise. And that's 2.5. So our new point is we went over 0.5, so we're over at 1.5, and we have a y of 2.5, right? Because every time we're moving over 0.5. So we're almost there. We're trying to get to y of 2, remember? So we'll plot that point. There's that point right there. Okay, so we plotted that, and we got one more time to do it, okay? 4 times is all we're going to have. So we need to calculate our y prime, so we put our 1.5 in there times 2. 1.5 times 2 is 3. We take our slope times our step size. 3 times 0.5 is 1.5. So our rise is 1.5. We're going to add that on to our old y and get 4. And so we now know that, and now we're done right there, right? We're done. We now have y of 2. So we don't have to finish this line. We now know when x is 2, we got y to be 4. Now what was y really? What was y of 2 really? It was 5. Ours is not enough. Ours is 4. Ours is off. Just like our areas were off. Why is it off? Well, they're not rectangles though. But I mean, I know what you're saying, but because what did we do? We assumed at each step the slope stayed the same that whole time, when in reality it didn't. The slope actually increased during those intervals. How can we make it better? Smaller steps. More rectangles, right? But they're not rectangles, but smaller steps. Narrower rectangles, right? So if we graph that, and here's the exact solution. They did a weird thing with the dx, don't worry about that. We already did this, y equals x squared plus 1. There's y equals x squared plus 1, right? So the whole time that slope was increasing as we went across. We were assuming that it didn't, and then we recalculated. So we went to a new point, recalculated the slope, said, oh, now it's going up. Recalculate the slope, now it's going up more. Recalculate the slope, right? Smaller steps would have been better, okay? That is Euler's method. Okay? All right. More accurate if a smaller value is used. It's less accurate as you move away from the initial value, the farther you move away. Okay, the Inspire has Euler's method built in. So let's get your calculators out. And I don't want to do that example right now. I want to do, so let's get out of this. And let's just go to our calculator. And let's now do it with those 4 steps just to see. And then let's do it with 10 steps. Okay, so we're going to have to go to our graph screen. And we're going to go to our menu and our graph entry. And we're going to go down here to differential equation, number 7. Everybody's got to be able to do this on the quiz next week, or on Friday.
Will you say that again?
Yep, go to the graph screen, go to the menu, go to the graph entry. Normally we go to function mode, right? Sometimes we went to parametric mode. Now we're going to go down to differential equation mode, which is number 7. And we've done this before, actually. I think we've done differential equation. Okay? So it looks like this. Now, if you have something in there, delete it out. But what you have is y1 prime. You can barely see it, but there's a little prime right here. That's the prime. So this is y1 prime. Now, we got to be careful then, because anytime we do a differential equation, it's got a y in it, we got to type y1 or y2 or y3, whichever one you're in. Now, it's usually y1 because we usually just do one at a time. Okay, there's a place right here for your initial condition. So in this one, we're going to put 2x. Now, you always got to wonder, am I using t? Because a lot of times differential equations have t's in it. But on the calculator, you can tell, because look at your initial condition right here. It says x and y1. So you're using x, not t. Parametric mode uses t. Our function mode uses x. Differential equation mode on the calculator also uses x. Okay? So if I had a differential equation about population, if it was p prime equals, and then it had t's, if I was going to graph it, instead of p, I'd have to use y1, and instead of t, I'd be using x. Okay? So understand that. All right. Let's put in our x then, and let's put in our initial condition of 0 and 1. Now, here's what we got to work with our window a little bit, and we've got to work with our settings. So if you would just keep hitting tab until those 3 dots, whoops, darn it, hit tab. Mine went to the graph, and yours probably did too. I want you to highlight that. Now, you can use your trackpad if you want to move over to it. But the little thing with the 3 dots, edit parameters. I want to get that highlighted and hit enter, or just click on it with your trackpad either way. Oh, the right arrows? The right and left arrow, good. And the up and right, yeah, you can arrow around. That's a good idea. That's probably the easiest. Notice the first choice is solution method. Now, if I do the little pull-down menu, I got 2 different choices, Euler and Runge-Kutta. Okay? Think of Runge-Kutta as just a better version of Euler. Think of Euler's as left and right rectangles, and think of Runge-Kutta as Simpson's rule. It's more complicated, but it's more accurate. We're not going to do it. Okay? What the heck? Let's do the worst one. It's easier to understand. So we're going to do Euler. Okay, that's what we're going to mess with. But if you really cared about getting a really good approximation, just like Simpsons would be better than left rectangles, Runge-Kutta is better than Euler. But we're going to do Euler. This, leave the same. You really won't have to go to this ever again, probably. Slope field, we'll just leave that. The plot start, plot end, the plot step, field resolution, 14. If yours all say that, you're good, and we probably won't have to go in here again. Okay? All right, but I just wanted to show you how it says we're doing Euler's method. Now, notice there's just a series of dots here. And I think I told you this last time when we did differential equation. Your calculator is really not solving this and graphing the x squared plus 1. It's plotting a bunch of points. And guess how it's getting those points? How's it getting those points? How's it getting those points? Take a wild guess. Yeah. How's it getting those points? How do we get those points in the table? You said table. Euler's method. Yeah, Euler's method. one's getting those points, right? Euler's method, right? That's what we did in those settings. You don't have to change any of the settings, Jamie. They should be. But
Mine was weird.
yours were weird.
No, mine was.
Really? Oh. Okay, we'll fix that. If you don't have the red curve, we'll fix that. Okay, solution method should say Euler. That should be a 1. Field should be slope. Are these all off? Or dimmed out? And then plot start, -10. Plot end, 10. Plot step, 0.1. Oops.
Was that 14?
Field resolution, 14. Those 3 dots in these 3 dots right here.
Whoa.
Yes.
Oh, I'll get that
Oh, yeah, because the window might be off. Yeah, because we haven't messed with the window yet, right? So, okay, so go back to menu. Yeah, no, it's good. We got to get these these questions answered. You're right, because we want it to work. -10, and plot end was 10. That's fine. I'm not sure. Then keep going down 0.1 and then 14. Yeah. Okay, go to a zoom standard would be a good start, and then now are we seeing? So if you go to menu and window and do a zoom standard, is everybody getting this? Yeah, different color would be, okay. Okay, getting that? All right, now, but again, notice there's a bunch of dots. That's because what it's doing, because we've told it to do Euler's method, and it's calculating those series of dots. Now let's do a window that's a little closer to what we just got done doing with our example. So let's go over here to menu and window settings, and let's start our X at say -1. And let's start our X max. Let's have our X max only go to about, what are we going to go to? We're going to go from 0 to, on our X. 5. No. Then we go to 2. So let's go 1 past that. Let's go to 3. Right? Remember, we were finding Y of 2. Right? Is what we were doing. So we were going to an X value of 2. And then on our Y window, of course, to do this, you got to kind of know something about it. I don't know if Zoom Fit is a great one on this. I'm not sure in differential equations how well Zoom Fit works. Let's try it. Let's just do it. What the heck? Let's just do a Zoom Fit and see what it does. I'm not sure on differential equations. That's pretty good. It's pretty good, actually. It went clear over here to 11. I don't know why. I had put 1 and 3 in there. So actually, now that I say that, I don't like it as well. Let's go into our menu, and all I'll do is change I'm going to change that back. I don't know why that went to 11. I don't like that. Let's go to 3. And then my Y certainly doesn't need to go that big. What kind of Y values were we at? 5? Let's go to about 9, maybe. And I probably don't add -9. I can keep that. That's fine. That's a little better. That's a little better. Okay.
How far up?
I went to 9 for my Y bands. Now there is one other thing in the window settings I guess I didn't do. I should have scrolled down a little farther, I think. Oh, you know what? No, I can't. I take it back. I'm sorry. We are going to have to go into those dots. Because the plot step, yeah, I forgot that. Remember, we said plot step was 0.1. What's our plot step on this? We called it the step size.
0.5.
It's 0.5. Yes, that I knew there was a reason I thought there was a reason we had to go into that. Whoops. So let's back out of that. So tab, get into here. Why is it? Oh, not tab. Yeah. Can I get that? There we go. Okay, get back into here. Now, which you can go up to menu and the graph entry, you can get to it again, or just tab usually takes you there. Let's go into those 3 dots again, those parameters, and let's arrow down here or tab down, and let's change that plot step. That's the only thing we should ever have to change in here, really. I think the -10 to 10 is going to be fine for any graphs that we do. Okay, and let's change that to 0.5. Okay, that's better. A lot less dots, right? There's fewer dots here. Okay, now let's trace. So this is the part where you use a calculator. So let's back up. We've done a lot of messing around here. So if you're actually doing this on the quiz, you have to do the calculator part. You go into differential equation, you put in your graph, you put in your initial condition, your equation, you put in your initial condition, you go to the 3 dots and put in your step size, right? And then you'll trace, which is what we're going to do right now. We'll start it from scratch here. So let's go to menu, and let's go to trace, and let's go to graph trace, and I'm going to go back 1 dot. I'm going to go arrow back, and so there's 0, 1. Right? That was the first entry in our table. Everybody there on trace now? So there's 0, 1. Then we're going to go to the right. 0.51. Isn't that the same point we had in our table? 0.51. What was our next point? 1 and 1.5. And then it was 1.5, 2.5. And then it was 2, 4. So really, if I was using my calculator, I didn't care about any of those other ones. All I care about is this last one, right? The question was, use Euler's method to find y of 2, or to approximate y of 2. So we did it with the table, so we want to be able to do that. And now we just did it with the calculator. We got 4. Now, you're only really supposed to use a calculator when you have double-digit steps, right? So back here, use 4 steps to find y of 2. I would write y of 2 is approximately 4. That's what I would say. We know y of 2 is actually 5, but it's approximately 4 if you use 4 steps, right? So when we graph that difference equation, it's important to understand when you trace, those are not exact solutions you're finding. We were doing that earlier this year. Those were not exact solutions. Okay, the exact solution is actually that. More steps would be better. So what's the only thing I have to change here to do 10 steps? Because I read 10 steps, I'm like, aha, I get to use my calculator here. I don't have to do a table. So step size, what are we going to do? It's going to be 2 minus 0, right? B minus A. Here's your B and A actually here, the 2 and the 0, right? 2 minus 0 divided by 10, which is 1/5 or 0.2. So we're going to go to our calculator. So if we were starting this from scratch, right, we would go into our differential equation mode. We would go to here, we would put in our differential equation, which is y prime equals 2x. We would put in our initial condition, 0, 1. We would go to the 3 dots over here to edit the parameters. Let's do it. Let's go down and change our plot step from 0.5 to 0.2. Hit enter. Trace. Now mine happens to actually already be there, and yours probably will be too, because we had just got done doing that. But normally it probably would have been back here. So I wouldn't, matter of fact, I'm going to do that. I'm going to go backwards here. I'm going to hit my left arrow and go back to the beginning and just look. So now if I would make you fill out that table with 10 of them, which I'm not going to, we'd have got 0, 1, we got 0.21, we got 0.4 and 1.08, 0.6. Now look right here. We had 1 and 1.8. What did we have when we did it? We had 1 and what? 1.5. See how it's more accurate? It's going up faster. Even though it's not as much as it's supposed to be, it's still better. And then we get all these, and sure enough, at 2, we get 4.6, which is closer, isn't it? We know the actual answer is 5. We're a little behind because every time we're assuming the slope is staying the same for those runs of 0.2 when it's really not. So it's not as accurate, but it's better. And so here we would say y of 2 is, so on the quiz, this is all you would have to put, right? That's all you would have in a problem like that. If I say use 10 steps to find y of 2, all you would do is go to your calculator, set the step size, boom, 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 trace to y of 2, and write down that answer. That's all you do. Okay? If it's fewer than 10 steps, then we're going to draw the table of Euler's method. So we hopefully understand how it's works. Okay? Both of those are not quite the same as that, but hopefully you see a little bit how this ties together with rectangle approximations and so forth. Okay, so a lot of the ideas of calculus, I mean, these are very different things. Finding the area under a curve and solving a difference equation, they couldn't be much different. And in the 1700s, they were very different. But when they started seeing the connections between them, guys like Newton and Leibniz and those guys started seeing the similarities of the connections. That's where this all got tied together as and became was called calculus. Okay, because of their similarities. All right, so let's review one other thing that you're going to be asked in the homework. This verify. Remember when it said verify that something is a solution? Show that y equals x squared plus 1 is the exact solution of this. So what we did is we took our differential equation. This is a real easy one, but we had something a little trickier. Show that this is actually the solution. Well, on this side, we'll do the derivative. Well, what's the derivative of x squared plus 1? 2x. Oh. Right? I mean, this one couldn't be any easier. We know we had some that were a lot more challenging than that, but we were basically showing that, oh yeah, the two sides are the same. Now, there's one part that I'm missing. We also got to show that initial condition works. So we also have to say, okay, if y equals x squared plus 1, if I plug a 0 in for x, I got to show that I get out 1. So I'd have to have that there as well. I have to show that this initial condition actually does work in there, right? Because if this would have been x squared plus 7, this still would have worked. The derivative still would have been 2x, but y of 0 equals 1 would not have worked if that was x squared plus 7, okay? So I've got to show both parts of that in showing that that's a solution. Okay, that's basically what your homework is going to be about. Here is, let me see if this is one of them. I'm thinking, no, this isn't. Okay, in your, so we won't go through this right now, but in your book they have this example. It was our Newton's Law of Cooling example. We take a hot cup of coffee, it's 190 degrees. Now maybe you recognize this as Newton's Law of Cooling. Remember the K out here? This was Y minus capital T. What was capital T? What temperature? The surroundings, the room temperature. So we got a 70 degree room, 190 degree cup of coffee. Here's the difference equation for it. How hot is the coffee after 5 minutes? Okay? So if I was gonna say to you, do this in 5 steps, and you're gonna write it out by hand, right? How would you start? Well, you put your initial condition here. I would just fill out the rest of this column. What would the rest of this column be? Isn't the width 1 here? Because you're going to go from 0 to 5, so that tells you you have a total width of 5, and you're going to do 5 subdivisions. So that's going to be 1. So the width is going to be 1. So you're going to have these 5 numbers down here, and then you guys just tell me, and you got your calculators handy. You don't have to write this down if you don't want to, but tell me how I would fill the rest of this out. So how would I get y prime? Plug what in?
0 to the y prime.
It's y, so I would plug the 190, right? I would plug the 190. If this had an x and a y in it, I might have to plug both things in, right? But you're right. You're going to plug this point, whichever parts fit, you're going to plug in. So do it on your calculator for me. So 190 minus 70, that'd be 120. Heck, we do this one in our head. Negative 1/10, won't that just move the decimal back 1? So that'd be negative 12. What do I do with that now? We've talked about a lot. We take that times the step size. What was our step size? 1. Oh, that'll be nice. That's just negative 12. So that basically tells me what? When I go over 1, I'm going to go down 12, right? That's what that line is saying. This is the rise. So that's telling me if I go over 1, I'm going to go down 12. Well, I was at 190, so the old y, take away 12, is 178. That means after 1 minute, the temperature is 178. Now, is it really going to be 178? No, because the slope is not going to be negative 12 for that whole 1 minute, right? It's actually going to slow down, right? Newton's law of cooling, it slows down how it goes. Okay, now let's do it on our calculator as some practice for that. So you could fill in the rest of that table, right? Okay, you don't have to. You're going to have a couple on your homework of different ones to do. Okay, but let's go back to the calculator just to practice this. So let's go to our menu. Let's go to our graph entry, differential equation. We still, of course, have this old one in, so we're going to have to get it out of there. So what do I want to type in here? Y1 prime equals what? Negative 0.1 parenthesis.
Y minus 70.
No. Y1. It's so easy to forget that. Y1 minus 70. You might try it without the 1 and see what kind of error you get. So when you end up getting an error, or maybe you don't get an error and you just get a graph, you'll notice that. And I'll probably help you with that. Well, no, I won't because I'm not going to be here on Tuesday. Well, I'll be here for part of it. So we have tracking. So I'll probably have left to go set up stuff. The UNK inventory, that's right. So negative 0.1 times y1 minus 70, and then we have to put our initial condition of 0, what was it? 190, and then we've got to go set our step size, our plot step, to what? 1. And I don't see anything. My window is no good because where did we start at? 0, 190, right? So I'm going to have to go to my window, and you're going to have to come up with this on your own. I may give you in the problem, I may give you some hints as to what to put, but 0, we can just start it at 0, and we're going to have to go up to 190 at least. Maybe we'll go 200 just for the heck of it. We do know, if you understand this Newton's law of cooling, we do know it's going to go down, but maybe you think, well, we're starting at 190, maybe it'll go up, so maybe you put 300 here. I don't know, whatever. Oh, that's the wrong one, though. Yeah, the X is going to go where? So maybe I'll put a 6. Yeah, we're going Y of 0. We're starting at 0, and we want to find the Y value at 5. Okay? And then I'm going to go here. I'll probably start that at 0, even though it's ridiculous, because is the temperature ever going to go down to 0? What's the lowest the temperature is ever going to be? Room temperature, but I'll just leave it at 0. That's fine. Maybe you didn't think of that. And I'll make this 200.
I think it's flat line.
Mine took a while to load because I also pressed standard.
Let me go back to my window. What's that? Our old friend Zoom Fit. And Zoom, and then it shows up.
The y-axis is
Times y1 minus. Okay, so Zoom Fit.
But yours is on.
What? Well, I have a 1 point on there.
No, there's
Oh, the whole thing loaded.
Yeah, mine took a while to load.
Oh, maybe it just took a while to make the calculation. Yeah, but try Zoom Fit. Yeah, it should work. We haven't had a problem getting them to show up. The ones on the quiz should show up fine. So now we go to trace, right? And we should see that. What happened? Menu, trace, graph trace. There it is. Okay, so let me back up. So 0, 190 was our starting point. and we just calculated the next one was 178, right? So that agrees. And then 2, and then 3, and then 4, and then 5. What happened? Oh, my screen moved over.
You guys have weird numbers. I like 157.48.
That's what I have.
Okay, did you set your plot step to 1?
Yeah.
Yeah, it's the way that we're.
Oh, if you zoom fit?
I'm zoomed out a little more. My axis is so bad.
This is weird. So let's go, I'm going to go -1 to 6. And I'm going to change my X scale to 1. I'm going to take off that auto. And then I'm going to go my Y min from 0 to 200. And I'm going to have this go by, I don't care, 50s. Doesn't really matter. That scale doesn't matter at all. Trace. God sakes, why is that stopping? Plot start to plot end, that's all good. Now see, now I got more points. So it's almost like when the points aren't showing up, I went into those 3 dots and I didn't even change anything, but when I come back, the points are there. But my points are all okay. That's what you should end up with. Is anybody getting?
Yeah, like, I have 140.859.
Oh,
It's just giving us one.
yes, okay, now I know what's going on there. Because we should have decimals. After that first one, we should have decimals. After the 178, are you getting the 178 on 1? I'll bet you are.
Yeah.
Yeah. See, mine, okay, I must have messed with my settings. See, I'm on float 3. Go to your menu. Go to your menu. Down here at settings, when you're in your graph, this should be just plain old float. And I'm pretty sure we had changed that. There you go, 140.859. Under settings, when you're on your graph screen, go to menu and then settings and make sure that says float. Your guys are probably okay. So you're good. So if you're getting those decimals, that's fine. So Casey's that what you were getting before, those decimals?
Yeah.
And you were right. Yeah. They should be decimals. Okay? Okay, good. So yeah, that was kind of interesting. We'll see on the homework. We'll be able to talk about tomorrow and see how things go on your homework problem. So if you look at your homework sheet, we're going to cross off 1 and 2. Well, what they are is they tell you to look back in one of the examples and then explain how this point was got. And I looked at that and I thought, well, it's the table. You just go through and do the table. So I don't want you to mess with it. So this is the last line on the homework, 6-3. So cross off 1 and 2. To make a few notes here, on number 6, they tell you to go back to one of the examples and in the book, and they give you a different initial condition. Okay? So they want you to then do 3 steps with a table with Euler's method. It says carry out 3 steps by hand. So do that, and then they ask you about it. So that's a little bit of practice doing it by hand, a couple steps. Number 8, when you get to number 8, is going to be one that you can find the exact answer. They ask you to do that. Then they ask you to do 5 steps with a step size of 1 of Euler's method, so you get some practice doing that. And then they ask you a question about what happened, what you see with your result, and you'll be able to think about that and get that. Number 11, and every one of these has multiple parts. I apologize, but actually it's fine because the first part. So on 11, the first part they say do 5 steps. So that means work it out with the table. Then part B says do 10 steps. So you just use your calculator. Okay? And then C, show the exact solution. So that was kind of that T-chart thing. So we get to just verify that it is. and then they just ask you a question about it. 13, actually, both of them you get to use your calculator. 13, part A says use 10 steps, part B says use 20 steps, and then show the exact solution. So there you can use just your calculator, so that's doesn't take very long. And then 15, one more time you get to do by hand 4 steps. And so that's about 3 times, I think it counted 3 or 4 times in there. You'll work them out by hand using the table. And then that's it. And then it asks you some questions about what happens with it. So you're investigating some things as you do them by hand. You kind of see some things. Okay. All right. So that's it for tomorrow. That Euler's method. Then tomorrow we'll have some work time and just review. We'll talk about all the stuff for the quiz. Kind of go back over some of the homework problems and say, hey, if you want to revisit these or these or these, that's what you want to know for the quiz. Then I'm going to give you your assignment for after spring break, basically, but you could probably get it done between your work time tomorrow and your work time after the quiz on Friday. You could probably, it's in sample 3. Basically, want to have the sample 3 packet done by when you come back from spring break. Okay? So you can probably get a lot of that done in the next 2 days when you're working on it. Okay?
We have so much to do.
When? That's what I'm saying. You'll get most of this done tomorrow in class. You can get most of it tomorrow in class. And then Friday after.
How do you get back till Monday?
All right.
I'll solve it. Yeah, I know. Yes, what? I can't. What do I get paid if it doesn't have you?